We present a novel method for tomography of refractive fields from a single viewpoint. Our work shows promising first steps towards several applications, including imaging the invisible dark matter throughout the universe. Refraction is the bending of light as it encounters a change in medium. When light hits this glass block, its path bends according to the difference in the refractive index between the air and the glass. Here, the refractive index changes only at a discrete boundary. However, we are interested in recovering fields where the refractive field is a continuous function of position x. When rays of light travel through these fields, they curve continuously in space rather than bending only at the boundaries. Continuous refractive fields appear in many places, including imaging hot gases and microscopy. We are motivated by weak gravitational lensing, in which massive clumps of dark matter bend the light that reaches us from faraway galaxies. Recent advances in imaging technology have made it possible to use these galaxies as a probe to measure the distribution of dark matter in the universe. We aim to reconstruct an accurate 3D map of its refractive field, which would provide a window into understanding the invisible cosmic web, which contains 85% of the universe's matter. Refractive fields are themselves invisible. In order to detect them, we must observe the refractive effects on visible light sources. The presence of a refractive field causes a warping effect on the light sources behind it. In the regime we are interested in, the degree of refraction is very small, causing subtle changes in the shapes of light sources. We are interested in solving the inverse problem of refractive field tomography. Given an observed refracted image from a single viewpoint, and knowledge of the distribution of light sources in a scene, we wish to estimate the structure of the refractive field underlying a scene. In refractive tomography, ray paths are both nonlinear and dependent on the structure of the unknown volume. Thus, refractive tomography is a nonlinear inverse problem which can be challenging to solve. As opposed to traditional CT, where ray paths are assumed to be fixed and known, the presence of a refractive field causes an unknown nonlinear effect on the ray paths. In addition, in our problem setting, we only have measurements from a single viewpoint. As opposed to previous works in 3D refractive tomography, which use camera setups covering multiple viewing angles, observing galaxies billions of light years away can only effectively be done from a single viewpoint, which is Earth's location. As a result, the problem is highly ill-posed. We are able to address this single viewpoint limitation through a combination of two ingredients. In astronomy, the locations of galaxies can be estimated with spectroscopy. Thus, we assume knowledge of the locations and shapes of dense point-like light sources located throughout the volume. This helps us to supervise the reconstructed volume spatially. In our work, we also use a neural representation of the 3D volume, which has been shown to give a good implicit prior for a wide range of ill-posed inverse problems. To solve this inverse problem, we use a coordinate-based neural network taking a 3D position x as input, which outputs a refractive index for that point. That network then represents a predicted refractive field. Next, given our neural refractive field, we ray trace using the iconal equations to determine the ray paths from the sensor. Next, we solve the radiative transfer equation to determine pixel intensities, which produces a predicted image. Our model is fully differentiable, allowing us to efficiently compute gradients of the pixel values with respect to the neural field parameters. The full model optimization pipeline is shown here. Throughout training, we use an image loss of the predicted image from our neural refractive field against the true observed image to optimize the weights of the neural reconstruction using gradient descent. Using our approach, we can recover randomly generated refractive fields given single viewpoint measurements of a dense field of light sources. However, due to the ill-posedness of this problem, our method can still be susceptible to artifacts in the reconstruction. Existing refractive tomography methods can recover refractive fields accurately given multi-viewpoint measurements, but are susceptible to back projection artifacts in the single view setting. However, our method can accurately recover refractive fields with single viewpoint measurements. When the light sources are located behind rather than throughout the volume, we can recover the shape of the compact gas plume, but our neural field places it in the wrong location. Finally, we apply our method to image a refractive field corresponding to a realistic simulation of dark matter with idealized measurements. We are able to fit a signal which causes sub% changes in observed pixels intensities to accurately recover a dark matter refractive field. Although just a first step, this result demonstrates promise in using our approach for mapping the distribution of invisible dark matter throughout the universe in the future. Thank you for listening. Please visit our project page for more details.